Okay. So good day, everyone. Today we are going to discuss about probability theory, some basic terminologies about the probability, right? So it is one of the topic that will be covered in the statistics, your subject of statistics for geoinformatics, right? It is one of this section. So we will do the introduction, then we will discuss about different terminologies that are going to be used in probability and theories related to it. Okay, so let us proceed with the introduction. So probability and statistics are the two important concepts in the math. Probability is all about chance, whereas statistics is more about how we handle various data using different techniques. How do we collect, organize, represent the data, and how do we analyze the data? Okay, that is the purview of statistics. Then it helps to represent complicated data in very easy and understandable way. Okay, so probability is all about chance, and statistics is about collecting, organizing, manipulating, and analyzing the data. So in this session, we will learn about some basic terminologies that are used in probabilistic theory in statistic, different types of probability, what are set, subset, sample size, etc., sample space, etc., and then different set operations, then some basic definitions in probability theory. Okay, so there are two types of probabilities. One is there are two types of terms. One is deterministic, another one is your non-deterministic. So what is deterministic phenomena? There exists a mathematical model that allows the, the perfect prediction of the phenomena's outcome. Then many examples exist in physics, chemistry, right? The exact science, where we can accurately predict the outcome of an event or of an process, right? That is your deterministic phenomena. Then there is non-deterministic phenomena. No mathematical model exists that allow perfect prediction the phenomena's outcome. Okay, so there is in deterministic phenomena, no mathematical model exists that allows perfect prediction of the phenomena's outcome. So your non-deterministic phenomena may be divided into two groups. One is random phenomena, another one is haphazard phenomena. Your random phenomena is unable to predict the outcomes, but in the long run, the outcomes exhibit statistical regularity. Okay, so for case to case basis or for step for, for each step or for individual or for the short run, uh, there will be no uh, regularity, there will be no sequence. All the uh, outcomes will be haphazardly distributed, sorry, will be randomly distributed, right? So it will be you will be unable to predict for the short run. But if you look at the data in the long run, okay, if you take data for a very long period, then you will see that that there is some statistical regularity, and based upon that regularity, that pattern, you can make predictions. Whereas in your haphazard phenomena, unpredictable outcomes will be there, but no longer an exhibition of statistical regularity in the outcome. Okay, so same as that of random phenomena, you will be unable to predict the outcomes. But here, there will be no statistical regularity or pattern even in the long run. So this type of phenomena is known as haphazard phenomena. Okay, so you will be unable to predict the outcome in both the cases. But in random phenomena, in the long run, you will be able to see some statistical regularity, some pattern. But in case of haphazard phenomena, even in the long run, you will not be able to see the statistical regularity. So your non-deterministic is again divided into two, that is haphazard and random phenomena. So in haphazard phenomena, unpredictable outcomes will be there, and no longer an exhibition of a statistical regularity in the outcome. That even if you take the data, the output in the long run, even then you will not be able to detect any statistical pattern. Okay, so do any such phenomena exist? Your haphazard phenomena, we will see. And will any non-deterministic phenomena exhibit long-run statistical regularity eventually? Okay. So here they are asking that, do such phenomena like haphazard phenomena do exist? And in the last one, they are asking that phenomena like a random phenomena, do those type of phenomena exist or not? That in the short term or in the short range, you will not be able to predict the outcome, but for the long run, such phenomena such phenomena for the long run, you will be able to see the statistical pattern or statistical regularity. Do these type of phenomena occur? Okay, in random phenomena, unable to predict the outcome, but in the long run, the outcomes exhibit statistical regularity. We have read it several times. So, for example, you are tossing a coin. uh, What would be the possible outcomes in that case? Either head or tail, right? So, for each toss, you will not be able to guess or predict what is going to be the output for each toss, right? But for the long run, for uh, 50 or 50, 60, or for any uh, uh, number of tosses, for large number of tosses, you can make an guess that the number of heads and the number of tails are most probably going to be 50-50, about 50-50, right? So for the long run, for the long term, you will be able to see the statistical regularity, or see some will be able to make some prediction. But for short term, or case for case to case basis, you will not be able to uh, make out the pattern. So this is an example of your random phenomena. Let us see another example. We are rolling a dice. What will be the possible outputs? One, two, three, four, five, six. These are the six faces that you will see on a dice, right? And it is enclosed in the curly brackets. So these curly brackets is the symbol of set. Okay, so This is the set of all the possible outcomes of an event of an event in which you roll a dice. So these are all the outcomes that you can get. Okay. So unable to predict outcome. So you will be unable to predict outcome for each role. But when we are talking about long run, that or in other words that 40, 50 or 60 times a dice has been rolled, then you can guess uh, with certainty or with a little bit confidence that yeah, the uh, that for every output the chance to occur is 1 by 6, right? The chance for the every output to show up or to occur will be 1 by 6, right? So here again you can see that for each role to role basis or for the short term you cannot make a guess that what is the outcome is going to be. But for the long term, if you are talking collectively about 40 to 60 rolls of a dice, then you can safely say that yeah, one the probability or the chances of one occurring is going to be 1 by 6. Similarly for all the other outputs, right? So unable, you will be unable to predict outcome, but in the long run, one can determine that each outcome will occur 1 by 6 of the time. So we are using basically symmetry. So in this type of example, in this example, the distribution of the output is even, means every output has the equal number of chances being selected. Okay, so if you will try to make the graph of the chances each output is having of the selection, okay, so your graph would be like a straight line parallel to x-axis. Okay, each has equal chance of being selected. Let us look at some definitions. First one is your the sample space. So your sample space is basically the set of all the possible outcomes that you can have, that you can get. So the set of all the possible outcome is going to be the sample space. So suppose if we are rolling a dice, all the outcomes that could use that could be possible, okay, that would be possible would the output would be all the outputs that are there when you roll a dice. All the values 1, 2, 3, 4, 5, 6 is known as sample space. Okay, so the sample space S for a random phenomena is the set of all the possible outcomes. So when you are tossing a coin, what could be the possible outcome, head or tail? So set of these outcomes, head or tail, is going to be your sample space, and the sample space is represented by capital S, and these curly brackets are representing the set. So if you are rolling out a dice, then again outcome will be, the possible outcomes are 1, 2, 3, 4, 5, 6. So this is your sample space. Space is uh, your sample space is having all the possible outcomes. Then comes the event. What is an event in probability theory? And this event is this event will be represented as capital E. You will see this capital E in many different places for the probability theory. Okay, so the event that is capital E is any subset of the sample space, that is any set of outcomes of the random phenomena. Okay, so your E is the subset of the sample space. So suppose if we are looking at this Venn diagram, so this square is representing your sample space as all the possible outcomes, and your event E will be a subset out of this whole subset out of this whole set. Okay, your E will be the subset. So E is any subset of the sample space, that is any set of outcomes, not necessarily all the outcomes, okay, of the random phenomena. So the event E is said to have occurred if after the outcome has been observed the outcome lies in E, right? So when can we say that event E has occurred? That after observing the outcomes, you find out that the outcome lies in the subset E. Then you can say that event E has occurred. Okay. For example, suppose you are rolling a dice, and event E is the uh, even numbers are being even number is the outcome, that is the event, that even number is the outcome, right? So when will you say that this event has happened? If you are getting an output, that is if you are getting an output that could be any of the element belonging to the this particular event, that is the that is even number as the output, right? So even if you are getting 2 or 4 or 6, it is it is the example of it is the example of the occurrence of event E. Okay, it represent event E, that event E has occurred. Event E was an even output when you roll a dice. Okay, well, let us see with some examples. So you are rolling a dice. Outcomes could be all these six values: 1, 2, 3, 4, 5, and 6. Right, set of this. These all the possible outcome. This is your sample space when you roll a dice. And suppose is the event that an even number is rolled. Right. So what would be the elements or output in that particular event E? Those will be 4, 6, 2, 4, and 6, right? So this is the subset of your sample space. 2, 4, 6 is the subset of your sample space. So this is an event. So when can we say that event E has occurred? That when you are rolling a dice, either you are getting 2 or 4 or 6. So after the observation, if you are seeing that you are getting an output that lies in this event E, then only then you can see that event E has occurred. Then there are some special events: the null event, the empty event. Okay, it is denoted with the phi, and or equal to your empty curly brackets or empty set. This is your null event. So null event means the event that contains no outcomes. Then entire event, the sample space S. So your entire event is your sample space S. So S, the event that contains all the outcome, is your sample space, right? So the empty event phi never occurs. The entire event S or sample space always occurs. Now let us proceed with some some of the elementary set operations that are going to be used in the that are going to be used on the events and probability theory. So your first one is union, right? So let us suppose A and B are two events. Then the union of A and B is the event. That event is denoted by A union B and is defined by A union B is equal to set having the elements E and that E belongs to A or E belongs to B. Okay, so the subset of the output or the subset of the output that belong to A union B could be the elements that belong to A, or it could be the elements that belong to B. Okay, so your subset is acting so your union is acting as OR function, right? Or that e- either you are getting the elements from the set A, or you are getting the elements from the set B. So your union act as OR. The event A union B occurs if the event A occurs and the event B occurs. Okay. Then comes the intersection. So as the name suggests, this event will only be considered to happen the element if the output is if the output belongs to the portion or the elements that are shared between A and B. Only then we will say that this is your intersection. Okay, so let A and B be two events. Then the intersection of A and B is the event, which will be denoted by A intersection, symbol of intersection B, and this intersection is defined by A intersection B equal to E, equal to set of E, and E belongs to A and E belongs to B. Okay, so what will be the elements or what will be the outcomes in the subset of A intersection B? What will be the outcomes? It will be the numbers in the numbers in this sample space that are common, or it is the output in the sample space that are common to both subset A and subset B. Okay, so your intersection act as AND operator. So the event A intersection B occurs if the event A occurs and the event B occurs. Okay, if both the events are occurring, only then we can say that event A intersection event uh, B. So event A and intersection B is occurring. Okay. Now comes the complementary set. So let A be any event, then the complement of A is denoted by A bar, and it is defined by A bar equal to set of E where E does not belong to A. So if any other value or any other output from the sample space that is not also the member or element of set A. Okay, so then we can say that event A complement has occurred. Okay, if you are getting the output, if you are getting the output and if you are getting the output that is not contained in set A, okay, but to the sample space but not to set a, then we can say that a complementary event A bar has happened or has occurred. Okay, the event A bar occurs if the event A does not occur. Okay, so these are exclusive events. What are exclusive events? We will see in the next slides. So in problems, you will recognize that you are working with union, right? If you see the word or, okay, so if you are seeing the word or, that means you are working with the union, okay, and then you are working with intersection. And if you are seeing the word not, that means you are working with the complement. Definition of mutually exclusive event. Then what are mutually exclusive event? B, and they do not, and if we draw their Venn diagram in the sample space, and if they do not overlap with one another, or if their outcome of their intersection is zero, if they do not uh, have intersection, any overlap, then those two subset will be termed as, or those two events will be termed as mutually exclusive events. Okay, so two events A and B are called mutually exclusive if A intersection B is null. This is your null set. Okay, and you can see in the Venn diagram below that A and B are not overlapping with each other. Okay, so when your A and B in the sample space are not overlapping with each other, then these two events will be termed as mutually exclusive. If two events A and B are mutually exclusive, then they have no outcomes in common, right? So because they are mutually exclusive, they are not overlapping with one another. So the, there will be no member column. There will be no common members between A and B, right? So that is why they are mutually exclusive. They have no outcomes in common. They can't occur at the same time. So when because they are mutually exclusive, they do not share even a one element or even one member. So when event one event is happening, that means other event is not happened. When other event has happened, that means the first one has not happened, right? Because they both have different elements. So if one element is the output, then the other event has not is not happening or has not happened, right? So now let us come to the probability. So definition of probability of an event is, suppose that the sample space S is equal to O1, O2, O3 up to On. O here is representing outcome. Okay, so suppose that a sample space has a finite number n of the outcomes. Also, each of the outcome is equally likely because of the symmetry. Means that if you draw the graph of their distribution, the graph will be a straight line uh, that all the outcomes are equally likely. That each and every outcome has equal number of chances for being selected. Okay, that is what it is meant by outcome is equally likely. Then for any event B, okay, so what is probability of an event E? That you have a sample space having the outcomes from O to O1 to On, and we are assuming that all the members have chance of being selected equal. So probability of the event E happening is the number of the elements in the event E divided by number of elements in sample space, or number of outcomes in sample space. So number of outcomes in E, total number of outcomes will be your probability. Okay. So the symbol N A is equal to number of elements of A. So, and here is representing number of elements, and here A is representing of the event A. Thus, this definition of PE, or probability of an event E, becomes probability of an event, that is PE, is equal to number of outcomes in the event E divided by total number of outcome in your sample space. So N divided by N, number of outcomes in E divided by number of outcomes, total number of outcomes. And this applies only to special case when sample space has finite number of outcomes. Right? So the graph drawn of the data distribution will be a straight line parallel to x-axis. That is what it is meant. What is meaning here with the term equiprobable. So if this is not true, a more general definition of probability is required. What are the various rules of the probability? One rule is the additive rule, or for the mutually exclusive event. Okay, so probability of the event A union B is equal to probability of A plus probability of B. That means we can also write it as probability of A or B, because as we discussed few moments ago, that your union will be represented by or, and complement will be represented by not. B, probability of A or B is equal to probability of A plus probability of B. So if this formula is only valid when these two events A and B are mutually exclusive. In other words, there is no common elements or no overlap between the event A and B. So in that case, your intersection of A and B would be phi, or the null. Okay, so if two events A and B are mutually exclusive, then they have no outcomes in common. They can't occur at the same time, right? So because when event A has happened, means event B has not happened, because B is not even in the same space. B has its own space. So if event A has occurred and there are two events A and B and they are mutually exclusive, then the outcome of the random experiment cannot belong to both A and B. So you can see here in the diagram that there are two events A and B, and they are not overlapping with each other, they are not touching each other, so they are mutually exclusive. So in that case, if you want to find out the probability of an event A union B, that can be calculated by taking the probability of individual event A and the probability of the individual event B. Okay, so this will be the formula when we have mutually exclusive events. But when we have mutually exclusive, inclusive, okay. So the rule of the additive rule. So in general, when you have two events and they are not mutually exclusive, then your formula becomes that is probability of A union B is equal to probability of A plus probability of B minus probability of A under intersection B, right? So this is the formula for the probability of an event A union B. Then we have minus P minus probability A intersection B. Why is that? Because suppose these two events A and B are they are not mutually exclusive, right? So and they are overlapping. So when we are adding the probability of both event A and event B, then we are actually adding the part that is the intersection between A and B two times, right? Because the same part is also included in A and the same part is also included in event B. So when we are adding only the probability of A and probability of B, then we are adding that particular particular event. So I will just subtract that from the equation. Okay. So what is the logic behind this? That A intersection B will give you this formula. So let us see in the Venn diagram. You can see that A and B are two events that are occurring in this sample space, and their overlapping portion is termed as A intersection B. When probability of A is added to probability of B, the outcome in A intersection B are counted twice, right? When will you try to find out the probability of A and B, right? A and B, then this intersection part will be counted twice. So that is why we are subtracting it with minus probability of A intersection B. Let us see for an example. Saskatoon and Moncton are two of the cities competing for the World University Games. There are also many others. The organizers are narrowing the competition to the final five cities. There is a 20% chance that Saskatoon will be among the final five. There is a 35% chance that Moncton will be among the final five, and an 80% chance that both Saskatoon and Moncton will be the final five. So, what is the probability that Saskatoon and Moncton will be among the final five? So, let us see with the example. Let A is the event that Saskatoon is among the 50%, right? Then let us see that the event that Moncton is among the final five. Okay. given probability of A is equal to 0.20 and probability of B is equal to 0.35, and probability of A underscore probability of A intersection B is equal to 0.08, that is 8%. So what is the probability of A union B? What is the probability? Probability of A union B is simply your probability of A plus probability of B minus probability of A intersection B. Okay, so that is giving you 0.47. So that is your probability of A union B. Rule of complements. Rule of complements mean that if you take the probability of A bar, that means A bar means not A. Okay, and if you add in that the probability of event A being happening, its outcome would be 1, right? So let A be any event, then the complement of A denoted by A bar is defined as A bar E. A bar is equal to the E, and E does not belong to A. The event A bar occurs if the event A does not occur, right? So these are always going to be mutually exclusive, such that A bar is happening, if A bar is happening, that means A does not happen, because these are mutually exclusive. So no area is interlapping, no area is overlapping. Okay, A bar and A are mutually exclusive. What is the logic behind this? So suppose A bar and A are mutually exclusive. So sample space is A union A bar. Okay. So sample space would be A union A bar, because A is the given subset and A bar is the rest of the outputs in the subsam in your sample space. Okay. So your probability of S, that is equal to probability of A union A bar. Okay. So one is going to the probability of your sample space, and it is equal to probability of A plus probability of A bar, that is equal to 1. So your probability of A bar is going to be 1 minus probability of A, because the total probability or the maximum probability is always going to be 1. Then comes the conditional probability. So what is conditional probability? Frequently before observing the outcome of a random experiment, you are given information regarding the outcomes. How should this information be used in prediction of the outcome? Namely, how should probabilities be adjusted to into account this information? So usually the information is given in the following form. You are told that the outcome belongs to a green event. You are told that a certain event has occurred. Okay, so you are told that the outcomes belong to a given event. So if you are told that a certain event has occurred. So what is the definition of this conditional probability? Suppose that we are interested in computing the probability of event A, and we have been told event B has occurred. So what would be the chance that event A is also occurred? occurred, then the condition probability of A given B is defined to be probability of A depending upon B is equal to probability of A intersection B divided by probability of B. So what is the rationale? What is the logic behind? So if you are told that the event B has occurred, then the sample space is restricted to B only, right? Because now we know for surely that B has occurred. So now all the sample size, all the outcomes that we are going to categorize will all fall inside the B now. So the sample space is restricted to B. The probability within B has to be normalized, right? Thus, it is achieved by dividing by probability of event B. The event A can now only occur if the outcome is in of the U section B. Hence, the new probability of A is given the probability of B is equal to probability of A intersection B divided by probability of B. Let us understand it with the example. So suppose there are there are 100 students in a class, right? So 60 are from Punjab, and some other number of students are from Haryana, and 20 out of them are from Chandigarh. So because Chandigarh is the capital of both your Punjab and Haryana. So the elements or the outputs will be distributed to both A and B. Okay. So if A and B are overlapping each other, some portion of it they are overlapping each other, right? We know that B has occurred. B has occurred. So B has occurred. So that means that sample space has the B. So what are the chances that, as I was uh, as we were taking the example of a class having 100 students, 60s are from Punjab and some given number, some numbers are from Haryana and 20s are from Chandigarh, right? What could be that? And it is given that five students have been, those are that of Punjab. Okay, those are that of Punjab. So, what would be the chance of A being selected also? So because now our sample space has restricted to the B itself, so the chance of A being selected would be the ratio of ratio of the subset ratio of the intersection divided by the total probability of set B. Okay, so the probability of A depending upon the condition of B is equal to probability of A intersection B divided by probability of B. So the example we were taking, so there were 60 student in a class from Punjab and some unknown number of students from Haryana and 28 numbers were from Chandigarh because Chandigarh is the capital of both the states. So the be counted in Punjab as well as in Haryana. Okay, so they in the we have assumed that five persons have been selected, and it is said that these five were from the Punjab. But you know that some portion of the Punjab is also overlapping with the portion of Haryana. How much it is overlapping? 20. 20, right? What are the chances that the selection that you have made of five students are not from that the selection that you have made is from that area? So you will just simply uh, divide the probability of A intersection B. That is, in our case, uh, number of number of Chandigarh from the student to the number of students from the Punjab, right? So 20 is the number of intersection or number of students from Chandigarh divided by the number of students from Punjab, right? That is 60. So that will give you 20 by 60 equal to 1 by 3. Okay. So that's it for today. We will discuss, we will continue with the probability in our next session. Okay. Thank you.